Deep within cosmic clouds, an invisible war rages between gravity and light. These stellar nurseries are violent factories where stars are born from chaos. By the end of this journey, you will understand the hidden forces that build suns and shape our very existence. How does a formless cloud of gas collapse into a brilliant, stable star? What determines whether a star will be a modest dwarf or a colossal giant? The answers reveal the spectacular drama behind every point of light in our night sky. What does our own sun's violent beginning tell us about our place in the cosmos? These vast molecular clouds are the universe's great construction sites, drifting like silent, dark islands in the galactic sea. Stretching for dozens of light years, a single one of these cosmic cradles contains enough gas and dust to forge tens of thousands of stars, but this is no serene haven. It is a realm of perpetual turmoil, where supersonic winds whip through the darkness and immense pockets of dust blot out the light from the stars struggling to be born within. The very material that will become new solar systems is also the shroud that hides the violence of their creation. This is the essential paradox of a stellar nursery, a place where the seeds of light are sown in absolute darkness. We can see this drama play out in nearby nurseries like the magnificent Orion Nebula, a glowing cauldron of gas where infant stars blaze to life, their fierce radiation carving away at the very cloud that birthed them. These nebulae are more than just factories, they are the ultimate recycling centers of the cosmos. The dust grains floating within them are rich with heavy elements forged in the hearts of long-dead stars, the legacy of ancient supernova now providing the raw materials for a new generation. This continuous cycle of death and rebirth is written into the fabric of every star, including our own sun. How does such a chaotic, diffuse environment ever give rise to the ordered structure of a solar system? The answer begins with a single, dominant force that eventually overcomes the chaos. This chaos has a name, and it is turbulence. Far from being mere random disorder, turbulence is the great cosmic architect, a structured and fundamental force that dictates the rhythm of star birth. Think of it as a stormy ocean on a galactic scale where immense waves of gas collide and churn. In the wake of these collisions, something remarkable happens. The gas piles up, creating dense, knotted regions that act as the embryos for future stars. These are the stellar seeds, born from the very violence that seemed to oppose them. The key player here is supersonic turbulence, a phenomenon where gas moves faster than the speed of sound within the cloud. This creates powerful shock waves that slam through the darkness, compressing vast volumes of gas into pockets dense enough for gravity to finally take hold. Without this relentless compression, the thermal pressure of the warm gas, its natural tendency to expand and dissipate, would win out and the cloud would never collapse. This chaotic process directly answers one of the great mysteries of stellar nurseries, why we see such a stunning variety of stars. The initial mass of a star, the amount of material it gathers at birth, is a direct result of this turbulent environment. A particularly dense knot, forged in a violent collision of interstellar waves, might collapse into a brilliant, short-lived blue giant. A smaller, quieter pocket may only muster enough material to become a modest, long-lived red dwarf. This distribution, known as the initial mass function, is a universal pattern set by the physics of chaos. The field of astrophysical fluid dynamics reveals how this turbulent energy cascades, transferring power from the largest scales of the cloud down to the smallest eddies. It is this inherent, structured disorder that populates the galaxy with the diverse stellar family we observe, from solitary dwarfs to dazzling binary systems. The very chaos that seems to resist star formation is in fact the creative engine that makes it possible, sculpting the unique identity of every single star that will ever shine. The tranquility of this turbulent chaos is always an illusion. Deep within these knotted regions of gas, a silent threshold is crossed. A pocket of the cloud, compressed by passing shock waves, reaches a critical density where its own self-gravity becomes too powerful to resist. This is the gene's instability, the precise moment when the inward pull of gravity finally overwhelms the outward pressures of heat and magnetic fields that had been holding the cloud apart. The balance of power shifts catastrophically and irrevocably. What follows is a cosmic avalanche, a runaway collapse where gas begins to fall inward, accelerating under its own weight. The center of this collapsing cloud grows denser and hotter with every passing moment, a gathering storm of matter and energy. But this collapse is not a simple, spherical implosion. The cloud was always slowly spinning, a remnant of the galaxy's grand rotation. As it contracts, this spin accelerates dramatically, a consequence of the conservation of angular momentum. It is the same principle that sees an ice skater spin faster as they pull their arms in. This forces the infalling material to flatten into a vast, spinning disk around the nascent central core. This protoplanetary disk is the fundamental blueprint, the raw construction site from which not just a star, but an entire solar system will eventually emerge. Every planet, every asteroid, every comet in our own system owes its existence to this flattened disk of gas and dust, a structure born directly from the physics of a spinning collapse. This gravitational victory marks the true point of no return, the moment a stellar nursery transitions from a cloud of potential to a factory of reality. At the heart of this spinning disk, the true drama begins. The central core is no longer just a knot of gas, it is transforming into a protostar. As material continues to rain down from the surrounding envelope, the pressure at the center becomes almost unimaginable. This immense compression generates fierce heat, but for a while, a strange thing happens. The heat cannot escape. The core has become so dense that it turns opaque to its own thermal radiation, trapping the energy within like a cosmic pressure cooker. Temperatures inside this trapped, boiling sphere begin a relentless climb, soaring from thousands to millions of degrees. This is the moment a collapsing fragment earns the name protostar, an embryonic sun still gathering its mass. The structure of this newborn object is a thing of violent beauty. The growing protostar sits at the center of the storm, a dense ball of incandescent gas. It is encircled by that vast, spinning disk of material, the future building blocks of planets, and the entire system is still shrouded within the remnants of its parent molecular cloud, a thick blanket of dust and gas that hides these earliest stages from visible light telescopes. Yet this is not a simple, peaceful infall of material. Immense magnetic fields, twisted and amplified by the rapid rotation, act as cosmic highways. They channel ionized gas from the inner disk in powerful, focused streams that slam directly onto the protostar's poles. These fiery jets can stretch for light years, punching through the surrounding cloud and announcing the star's violent birth to the cosmos. We can witness this hidden drama thanks to infrared and radio astronomy. Instruments like the James Webb Space Telescope peer straight through the obscuring dust, revealing the warm glow of these infant stellar systems. They show us the glowing accretion disks and the brilliant, narrow jets in stunning detail, confirming the theoretical models of this chaotic construction phase. Everything about a star's future, its final mass, its temperature, and even its potential to host planets, is decided during this brief but furious protostellar period. It is a foundational chapter written in fire and gravity, a crucible that forges the basic identity of a sun for the rest of its life. This swirling disk of gas and dust is the protostar's lifeline. Acting as a cosmic conveyor belt, it funnels the raw material of the collapsing cloud directly onto the growing star at its center. But this process is far from straightforward, governed by a fundamental cosmic rule. As the cloud collapsed, its initial, gentle spin was amplified into a furious whirl, a direct result of the conservation of angular momentum. If all that spinning material tried to fall straight onto the star, it would be flung back out into space like a stone from a sling. The accretion disk is the elegant solution to this angular momentum problem. It is a flattened, spinning reservoir where material can gradually lose its orbital energy and spiral inward, finally reaching the hungry protostar. The key is friction. Particles within the disk collide and rub against one another, generating heat and a type of internal drag known as viscosity. This friction causes the outer parts of the disk to slow down slightly, while the inner parts speed up, creating a traffic jam of sorts that forces material to drift slowly inward over thousands of years. This constant friction heats the disk to incredible temperatures, causing it to glow with a warm infrared light that our telescopes can detect across the vastness of space. We see this beautiful, violent process playing out in nearby stellar nurseries like the Taurus molecular cloud. There, the Hubble and James Webb Space Telescopes have captured stunning images of these protoplanetary disks as dark silhouettes against bright nebulae, or as glowing rings of dust and gas encircling their infant stars. The dynamics within this disk are a cosmic balancing act with profound consequences. The rate at which material spirals inward dictates the final mass of the star. Too much too fast and the star could become unstable. Too little and its growth is stunted. But the material that does not make it to the star is not wasted. It is within this very disk that the seeds of planets are sown. Dust grains collide and stick together, eventually building up into pebbles, then rocks, and finally, the cores of future worlds. The accretion disk is the ultimate cosmic nexus, the critical interface where the fate of a star and the birth of its potential planetary family are decided simultaneously. But this furious construction process creates a problem the star must solve. As material spirals in from the disk, it brings with it an enormous amount of spin, a dangerous surplus of angular momentum that threatens to tear the entire young system apart. The star's brilliant solution is one of the most violent and beautiful events in its early life. It violently ejects a fraction of this incoming material, not in all directions, but in two incredibly focused, opposing jets that scream away from its north and south poles at nearly relativistic speeds. These are protostellar outflows, the star's powerful birth cries. Imagine a pair of cosmic blowtorches sculpting the surrounding cloud with unimaginable force. These are not gentle winds, but highly collimated beams of partially ionized gas, accelerated by magnetic fields that are wound up tighter and tighter by the star's rapid rotation. These fields act like the barrel of a rifle, channeling the ejected material into narrow, high-velocity streams that can stretch for light years, punching straight through the remnants of the molecular cloud that birthed them. Where these supersonic jets slam into the slower-moving interstellar gas, they create brilliant, shock-heated knots known as Herbig-Haro objects. These are the glowing bow shocks and turbulent wakes that mark the jet's path, visible to telescopes as luminous, ephemeral structures that change over just a few years. The Hubble Space Telescope has captured breathtaking images of these cosmic artworks, showing them as intricate, glowing filaments and cavities carved into the heart of nebulae like fireworks frozen in time. This violent expulsion is not wasted energy. It is a crucial regulatory mechanism. By flinging material away along its poles, the star efficiently carries away the excess spin that would otherwise prevent more material from falling onto its surface. It is a cosmic trade-off, sacrificing a small amount of mass to shed the dangerous angular momentum that inhibits its growth. This allows the accretion process to continue, enabling the protostar to keep gathering mass from its disk and ultimately achieve the core density and temperature needed for nuclear fusion. But the influence of these jets extends far beyond the star itself. They are powerful agents of feedback stirring up the surrounding nursery. The outflows inject tremendous energy into the cloud, simultaneously compressing some regions to trigger new star formation while dispersing other areas, effectively shutting down further birth nearby. These brilliant bipolar jets are far more than a spectacular light show. They are the fundamental tools a young star uses to sculpt its own destiny and influence the future of its stellar siblings, a dramatic announcement of a new sun forging its place in the cosmos. These magnetic fields are the silent conductors of the cosmic orchestra. They thread through stellar nurseries like an invisible skeleton, providing a hidden architecture that guides the chaos. Without these fields, a molecular cloud would collapse into stars far too quickly, resulting in a brief, furious burst of star formation that would rapidly exhaust the galactic fuel supply. Instead, the fields offer a form of support, a subtle resistance against gravity's relentless pull. This creates the theory of magnetically supported clouds, where the field lines are frozen into the gas, creating a springy framework that holds the cloud up and slows its descent into collapse. But this support is not permanent. Through a slow, patient process called ambipolar diffusion, neutral atoms of gas gradually drift past the stationary, charged ions that are locked to the magnetic field lines. This slow leakage allows the cloud to contract at a controlled, measured pace, ultimately permitting gravity to win in specific, dense regions. It is this delicate magnetic mediation that sets the stately, billion-year tempo of star formation across a galaxy, preventing a cosmic traffic jam of stellar birth. This magnetic scaffolding does more than just slow the collapse, it also sculpts the flow. As a core rotates faster and faster, its magnetic field lines are wound up into a tremendously powerful rotating structure. Think of a child spinning around while holding the end of a rope, the rope whipping out into a tight, spiraling coil. In the same way, the protostar's spinning magnetic fields act as a sling, flinging ionized gas outward from its poles. This is the magnetocentrifugal mechanism in action, a profoundly efficient engine for creating the spectacular jets we observe. Material from the inner accretion disk is funneled along these rigid field lines and accelerated to incredible speeds, creating the focused, bipolar outflows that carry away the star's dangerous excess spin. This process is not a gentle breeze, it is a tightly controlled magnetic catapult. We can now map these invisible architects directly. Astronomers use polarization, a property of light, to trace the orientation of magnetic fields within dark clouds like Barnard 1. As starlight passes through clouds filled with magnetically aligned dust grains, its waves become preferentially oriented. By measuring this subtle polarization, our telescopes can effectively see the magnetic field lines imprinted on the sky, revealing how they drape across the nurseries and guide the collapsing material. These observations confirm that the fields are not random. They have a clear, large-scale structure that channels flows and influences the very shape of the forming disks. The presence of a strong magnetic field can even suppress the formation of a large disk initially, forcing the system to evolve in a distinctly different way. From setting the grand timeline of collapse to directing the furious jets that clear its cradle, magnetic fields are the indispensable, unseen hands that shape a star's violent entrance into the universe. They complete the picture, transforming a story of pure gravity into a far more intricate and beautifully orchestrated ballet of force and form. Yet even as a star unleashes its magnetic fury, it awakens a second, more subtle power that will ultimately define its final size. This is the force of light itself. When a newborn star begins to shine, its photons, those tiny packets of light and energy, do not simply stream away into the void. Each one carries a tiny amount of momentum, and when these photons collide with atoms and dust grains in the surrounding gas, they give that momentum a push. It is a cosmic game of pool on an unimaginable scale, where countless gentle nudges from light add up to a significant outward pressure, directly opposing the inward pull of gravity. This is radiation pressure, the silent counterweight to collapse. For a star to keep growing, the inward flow of material from its accretion disk must overcome this constant pushing force of its own brilliance. This creates a fundamental and elegant limit to stellar growth, a concept known as the Eddington limit. This is the maximum luminosity a star can emit before the outward push of its radiation becomes so powerful that it halts further accretion, effectively stopping its own growth. Think of a star trying to drink from a fire hose of incoming gas, only to find that its own light is blowing that material away. The interaction between light and matter happens through several key mechanisms. For very hot, massive stars, the primary process is electron scattering, where photons bounce off free electrons in the ionized gas, transferring their momentum with remarkable efficiency. In dustier environments, like the outer regions of a protoplanetary disk, the process is different. There, photons are absorbed by dust grains. These grains heat up and then re-emit the energy in a different direction, effectively getting pushed along by the starlight. This is how intense radiation can literally blow dust and gas away from a stellar environment. We see this dramatic balancing act playing out with the most massive stars in the universe, the brilliant O-type and B-type giants. Their surfaces rage with such ferocious light that their radiation pressure becomes an impenetrable barrier. For these stellar behemoths, the very act of shining caps their mass, often limiting them to somewhere around 100 to 200 times the mass of our own Sun. Any further material trying to fall in is simply blown away by the hurricane of photons streaming from the star's surface. This radiation does not just regulate the star's growth, it also sculpts its entire neighborhood. The powerful stellar winds and radiation from a single massive star can shred its natal cloud, evaporating nearby gas pockets and preventing smaller, sibling stars from forming. In spectacular nebulae like the Carina Nebula, we see these massive stars carving out vast cavities and pillars with their intense light, simultaneously destroying the nursery that created them while triggering new waves of star formation at the compressed edges of these bubbles. This beautiful feedback loop, this cosmic dance between the creative force of gravity and the limiting force of light, ensures that no single star can grow to dominate the galaxy. It is a self-regulating mechanism written into the fundamental laws of physics, a delicate equilibrium that maintains the diverse and balanced population of stars we see glittering in the night sky. While the slow dance of gravity and light carves out modest stars like our Sun, the universe also forges true giants. The birth of a massive star is a different kind of event entirely, a violent and rapid genesis that pushes the laws of physics to their absolute limits. Where a star like our Sun may take millions of years to form, a massive O-type star can blaze to life in just 100,000 years. This breakneck pace is born of sheer chaos. In the dense, crowded cores of the most active stellar nurseries, a process called competitive accretion takes over. Here, the richest pockets of gas act like cosmic magnets, funneling a disproportionate amount of material onto a few privileged protostars. It is a stellar feeding frenzy where the biggest embryos grow the fastest, greedily pulling in gas from their surroundings and outstripping their smaller siblings. This is why massive stars are almost never born in isolation. They form in dense, glittering clusters where their fierce gravity and brilliant light will forever influence their stellar neighbors. This frantic growth creates a unique and paradoxical problem. A massive protostar gathers mass so quickly that its core ignites nuclear fusion while it is still actively feeding from its accretion disk. The star begins shining with unimaginable ferocity while it is still under construction. This creates a monumental struggle at its surface, a battle between the inward torrent of infalling gas and the outward hurricane of radiation pressure trying to blow that same gas away. For a time, the sheer weight and momentum of the accretion flow can overcome this intense light, forcing material through the radiation barrier and onto the star. But this cannot last forever. The balance is incredibly delicate and it dictates the ultimate ceiling for a star's mass. We can witness the climax of this struggle in regions known as ultracompact H2 regions. These are glowing, ionized bubbles of gas that mark the location of a newborn massive star. As the star switches on, its flood of ultraviolet radiation instantly ionizes the hydrogen gas around it, ripping electrons from their atoms and causing the gas to shine with a characteristic red glow. The star is literally burning its own cradle. These regions are small, dense, and short-lived, as the star's immense radiation and powerful stellar winds rapidly expand the bubble and dissipate the remaining cloud. Observing these objects gives astronomers a direct look at the precise moment a stellar behemoth announces its presence and begins to tear apart its natal environment. The formation of these colossal stars represents the most energetic and disruptive events within a stellar nursery. Their birth is not a gentle arrival, but a cataclysmic explosion of energy that sculpts the entire cluster. Their intense ultraviolet radiation evaporates the gas from nearby protoplanetary disks, potentially limiting planet formation around other stars. Their powerful winds and eventual supernova deaths will churn the interstellar medium, seeding it with heavy elements and triggering the next generation of star formation. To understand the birth of massive stars is to understand the upper limits of cosmic construction, the point where a star's own light nearly prevents its existence. This violent genesis reveals the extreme conditions that create the universe's most brilliant and short-lived giants, the engines that drive the chemical and dynamic evolution of entire galaxies. Our own solitary sun is actually an exception in a galaxy filled with stellar families. The chaotic physics of a collapsing cloud frequently produces not one star, but a gravitationally bound system of two or more stellar companions. These cosmic partnerships are born from the same turbulent forces that sculpt single stars. When a dense core within a molecular cloud begins to collapse, its internal turbulence can rip the fragment apart, causing it to split into two or more distinct embryos. This turbulent fragmentation seeds the cloud with multiple stellar seeds from the very beginning. Another common pathway unfolds a bit later in the process. A single protostar forms with a massive disk of gas swirling around it. This disk, if it grows dense and massive enough, can become gravitationally unstable. It begins to wobble and develop its own spiral arms, much like a miniature galaxy. Within these arms, dense clumps of gas can coalesce and collapse under their own gravity, forming a second or even a third star right there in the disk. This process of disk fragmentation often creates systems with a central pair of stars and a wider stellar companion that likely formed from the outer disk. The result is a spectacular diversity of stellar relationships, Some binary stars are so close they are practically touching, whirling around each other in a matter of hours. These are contact binaries where the two stars share a common atmosphere in a dizzying cosmic dance. At the other extreme, widely separated pairs take hundreds or even thousands of years to complete a single, stately orbit. The separation between the stars is a direct fossil record of the conditions within their natal cloud fragment, a permanent imprint of their chaotic birth. The likelihood of forming such a system is deeply tied to the stellar nursery's density. In the crowded, bustling cores of massive clusters, where protostellar disks are constantly jostled and fed by a rich reservoir of gas, binary systems are the rule, not the exception. It is in these dense environments that gravitational encounters between young stars can even capture passing singles into new, bound partnerships. Look up at the night sky's brightest star, Sirius. What appears as a single diamond is actually a brilliant couple, a luminous main sequence star locked in a 50-year orbit with a faint, dense white dwarf companion. This partnership has profoundly shaped their evolution. The white dwarf is the remnant core of what was once the more massive star of the pair. It lived fast, died young, and transferred some of its material to its companion, leaving behind the stellar ghost we see today. The prevalence of these systems is staggering. Astronomers estimate that at least half of all Sun-like stars in the galaxy are part of a binary or multiple star system. This simple fact forces us to reconsider our place in the cosmos. Our quiet, singular solar system, with its planets on stable orbits, might be the quieter outcome of stellar birth. The true galactic norm is a sky filled with multiple suns, a universe where most stars are born with a lifelong companion, their fates forever intertwined by the turbulent cradle that created them. The brilliant death of a massive star sends a final, violent gift back into the cosmos. When a star reaches the end of its life and explodes as a supernova, it does not simply vanish. It unleashes a titanic shockwave that races through interstellar space at thousands of kilometers per second, a wall of pure energy that slams into nearby molecular clouds. This is not an ending, but a cosmic domino effect where stellar death directly triggers the birth of a new generation. The expanding shell of the supernova remnant acts like a colossal snowplow, sweeping up vast quantities of gas and dust and compressing it into an incredibly dense, cold layer on its leading edge. Within this compressed shell, pockets of gas can be squeezed beyond their ability to resist collapse. The delicate balance that kept the cloud stable is shattered. Gravity, once held at bay by internal pressure, now finds its opportunity, seizing these dense knots and initiating the same runaway collapse that forges new stars. This process, known as triggered star formation, turns the aftermath of a stellar catastrophe into a stellar nursery. We see this beautiful, destructive cycle etched across the sky. Around supernova remnants like W44 and IC443, astronomers observe young, bright stars and telltale protostars lining the rims of the expanding bubbles. These infant suns are not there by coincidence. They are the direct descendants of the explosion, their birth catalyzed by the violent passing of their stellar predecessor. This creates a self-propagating chain reaction throughout a galaxy. One generation of massive stars lives fast, dies young, and explodes, their shockwaves carving into clouds and triggering the next wave of star formation. Those new stars will, in turn, eventually die and continue the cycle. This intricate feedback loop, this cosmic recycling of matter and energy, demonstrates a profound truth about our universe. The very elements that make up our world, the iron in our blood and the calcium in our bones, were forged in the hearts of stars and scattered by their explosive deaths. Those same elements, now enriched in the interstellar medium, become the building blocks for new solar systems and potentially new life. The grand story of our galaxy is not one of isolated events, but of a continuous, interconnected dance where the end of one stellar life becomes the catalyst for the beginning of countless others. This cosmic lottery of star birth follows a surprisingly predictable pattern. Across the galaxy, stellar nurseries produce a distinct family portrait, a distribution of stellar masses known as the initial mass function. This is not a random outcome. It is a universal probability curve that reveals a profound bias in the universe's construction process. The initial mass function tells us that for every single brilliant, massive star born, a stellar nursery will produce dozens of far more modest suns. The odds overwhelmingly favor the small and the faint. The most famous form of this rule is the Salpeter function, a mathematical description that shows the number of stars drops off dramatically as their mass increases. Think of it like a cosmic bag of marbles. If you reached in, you would be far more likely to pull out a small, common red marble than a rare, giant blue one. More modern versions, like the Krupa function, refine this picture, showing that the preference for low-mass stars is even more pronounced for the very smallest, dimmest stellar objects, the brown dwarfs. This distribution is not a suggestion. It is a fundamental law of stellar demographics, a statistical fingerprint left on every star cluster we observe. But how does such a consistent pattern emerge from the apparent chaos of a turbulent cloud? The answer lies in the delicate balance between competing forces. Turbulence within the molecular cloud first creates a spectrum of dense knots, a range of stellar seeds of different sizes. Gravity then takes over, but its success depends on the initial mass of these seeds. Smaller, lower mass cores are simply far more common and more stable. They can collapse without triggering the intense feedback processes that shut down the growth of their massive siblings. A large, massive core forms in an environment of fierce competition, where its own rapid accretion ignites fusion early, blasting its surroundings with radiation that eventually cuts off its own fuel supply. The initial mass function is, therefore, the natural outcome of this self-regulation. It is the statistical result of gravity's attempt to build stars within an environment that is constantly being stirred by turbulence and disrupted by the light of the newborn stars themselves. What is truly astonishing is the universality of this pattern. From the crowded heart of our Milky Way to the faint, primordial galaxies at the edge of the observable universe, the initial mass function appears to be remarkably similar. This suggests that the underlying physics of turbulence, gravity, and feedback are so fundamental that they produce the same mass distribution regardless of the specific environment. This consistency has profound implications for the entire life cycle of a galaxy. The initial mass function dictates the relative number of stellar giants versus stellar dwarfs, which in turn controls the galaxy's long-term evolution. Massive stars are the cosmic powerhouses. They live fast, produce immense amounts of ultraviolet light, and end their lives in supernova explosions that seed the interstellar medium with heavy elements. A galaxy that formed only low-mass stars would be a much darker, chemically simple place. It is the specific ratio dictated by the initial mass function that ensures a steady supply of these cosmic recyclers. The number of massive stars is just enough to enrich the galaxy without completely sterilizing it. This statistical rule, born from the violent cradles of stellar nurseries, ultimately writes the recipe for galactic chemistry and the very potential for planets and life itself. The clock of star formation ticks at wildly different rates across the cosmos. For a massive O-type star, the journey from a cold cloud fragment to a blazing giant is a breathtakingly brief sprint of only 100,000 years. This frantic pace is driven by an incredibly high accretion rate, a veritable fire hose of infalling gas that builds the star's bulk with astonishing speed. In stark contrast, a star like our own Sun takes its time, a leisurely construction project spanning 10 to 50 million years. This prolonged gestation is due to a much slower and steadier trickle of material from its protoplanetary disk. This dramatic difference in developmental pacing is fundamentally tied to the thermal timescale of the forming object. A massive protostar gathers so much material so quickly that its core temperature and pressure skyrocket, rapidly reaching the ignition point for nuclear fusion. Its immense gravity pulls in gas with such force that it can briefly overwhelm the fierce radiation pressure its own brilliance creates. A solar mass star, however, must wait. Its slower accretion allows heat to escape more effectively, keeping the core cooler for longer and delaying the final transition to a true hydrogen-burning star. This is why we find massive stars only in the very youngest clusters, still surrounded by the glowing remnants of their natal clouds, while their smaller, slower-burning siblings are found in older, more dispersed groupings where the gas has long since been blown away. These timelines are not just theoretical, they are etched into the stellar populations we observe in clusters of different ages. A very young cluster, like the one embedded in the Orion Nebula, is a bustling nursery teeming with protostars of all masses, many still shrouded in their dusty cocoons. Within a few million years, the most massive members have already blown away their birth shrouds and stand revealed as brilliant blue-white giants. Return to that same cluster after 10 million years, and those massive stars may already be gone, having lived their short, violent lives and expired as supernova. The Sun-like stars, however, are only just arriving on the main sequence, finally achieving a stable balance and beginning the long, steady burn that will characterize most of their lives. This creates a complex age distribution within any single stellar family, a snapshot of cosmic child development where siblings are at vastly different stages of maturity. A crucial milestone in this developmental journey is the birth line. This is the theoretical track on the Hertzsprung-Russell diagram where a protostar finally becomes optically visible, its surface emerging from the opaque envelope of dust and gas that has hidden it from view. The location of this birth line is a direct function of the star's accretion history. A star that has accumulated its mass rapidly will appear on the birth line as a much brighter, hotter object than a star of the same final mass that assembled itself slowly. This is because the rapid assembly traps more heat, leaving the newborn star more luminous and inflated. Once a star crosses this threshold and becomes visible, its subsequent journey to the main sequence is a process of gravitational contraction and gradual cooling, settling into its long-term stable state. The vast range of formation timescales, from a cosmic blink to a prolonged gestation, reveals a universe where mass is the ultimate dictator of destiny. It governs not only how a star will live and die, but the very pace of its entrance onto the cosmic stage, creating a rich tapestry of stellar ages in every corner of our galaxy. This final push to maturity is a star's true rite of passage. All the violent chaos of its birth now culminates in a single, stable, and self-sustaining fire. Deep within the protostar's core, a relentless contraction drives temperatures ever higher, crossing a critical threshold of approximately 10 million Kelvin. At this extreme, the core becomes a frenetic arena where protons, the nuclei of hydrogen atoms, now move fast enough to overcome their mutual electrical repulsion. They slam into one another and begin to fuse, igniting the proton-proton chain reaction. This is the moment nuclear fusion becomes the star's primary energy source, a self-regulating engine that will power it for millions or billions of years. The star has finally lit its central furnace. This ignition triggers a profound and lasting peace. The tremendous energy released by fusion creates an immense outward radiation pressure that pushes back against the unrelenting crush of gravity. The star achieves a perfect standoff known as hydrostatic equilibrium. It is no longer collapsing, nor is it expanding. It has found its balanced, stable form, a sphere held in a delicate cosmic tension that will define its long adulthood. This is the arrival on the main sequence, the stellar neighborhood where a star will spend the vast majority of its life. But for a star like our Sun, this final step into maturity is not a quiet one. It enters a tumultuous phase known as the T-Tauri stage. Think of this as stellar adolescence, a period of intense growth spurts and unpredictable mood swings. A T-Tauri star is wildly variable in brightness, its surface roiling with immense starspots and violent flares far more powerful than anything our modern Sun produces. It unleashes a powerful stellar wind, a continuous stream of charged particles that blows away the last remnants of its dusty protoplanetary disk, effectively clearing its cradle and announcing its independence. This powerful wind plays a crucial role in determining the final architecture of any nascent planetary system, blowing lighter gases away from the inner orbits and leaving behind the rocky building blocks for terrestrial worlds. The path a star takes to reach this stable main sequence is beautifully mapped on the Hertzsprung-Russell diagram. For stars of different masses, the journey looks completely different. A high-mass star, born brilliant and hot, makes a nearly horizontal dash to the left across the diagram, reaching its main sequence position quickly and with little fanfare. A low-mass star, however, takes a much longer and more dramatic route. It first appears as a luminous, inflated object on the right side of the diagram, then slowly contracts and dims over millions of years, moving downward and to the left until it finally settles onto the main sequence. These pre-main sequence tracks are like cosmic footprints, preserving the history of each star's assembly. The transition to the main sequence is the ultimate graduation. It marks the end of formation and the beginning of a star's true, independent life, a brilliant and stable beacon finally ready to illuminate the cosmos on its own terms. Yet this entire cosmic drama of collapse and ignition depends on a hidden ingredient, one written into the periodic table of the elements. The chemical richness of a stellar nursery, its metallicity, acts as a master control knob for the star formation process. Metallicity is simply the fraction of a cloud's mass that is made up of elements heavier than hydrogen and helium. In the modern universe, this includes the dust grains of silicon and carbon, the oxygen in water ice, and the iron in microscopic particles. These seemingly insignificant specks are far more than just raw material. They are the essential tools that allow a star to build itself efficiently. In the metal-rich nurseries of today's Milky Way, like the Orion Nebula, these dust grains perform a critical service. They are brilliant radiators of heat. As a cloud collapses and grows denser, the gravitational energy gets converted into thermal energy, heating the gas. If this heat cannot escape, the rising internal pressure will halt the collapse. This is where dust saves the day. The dust grains absorb this heat and re-radiate it away as infrared light, effectively acting as the cloud's air conditioning system. This efficient cooling allows the cloud to fragment into much smaller, denser cores, paving the way for the birth of a multitude of low-mass stars like our Sun. Without this dust-enabled cooling, the story of star formation would be profoundly different. We see this alternate reality when we look back to the dawn of the cosmos, to the era of the very first stars. These population 3 stars formed in a universe devoid of metals, a pristine environment of only hydrogen and helium gas. Without dust grains to cool the gas, the only cooling mechanism available was the faint glow of molecular hydrogen. This process was terribly inefficient, meaning the collapsing clouds could not shed their heat and fragment easily. The result was a cosmic monopoly on star formation. Theorists suggest that without efficient fragmentation, these first stars were likely behemoths, each one a colossal giant hundreds of times more massive than our Sun. They would have lived ferociously brief lives, burning through their nuclear fuel in only a few million years before exploding as titanic supernova, flooding the void with the first heavy elements. This initial enrichment forever changed the universe, seeding the primordial gas with the metals that would enable all future generations of smaller, longer-lived stars to form. The legacy of metallicity is written across the galaxy today. Compare the bustling, efficient star factories in the metal-rich spiral arms of the Milky Way to the quieter, more primitive dwarf galaxies that orbit it. These dwarf galaxies, like the Small Magellanic Cloud, have much lower metallicities. In these environments, the star formation process is less efficient and skewed toward higher masses. With fewer dust grains to cool the gas, clouds struggle to fragment down to the small scales required to make red dwarfs. The initial mass function in these metal-poor regions is top-heavy, producing a greater proportion of massive stars relative to low-mass ones. This chemical influence even extends to the fierce struggle between gravity and light. In a low metallicity environment, the gas is more transparent. There are fewer dust grains to absorb the photons from a massive protostar, which means radiation pressure can escape more easily. This might seem like it would help blow away the gas, but the effect is complex. This transparency actually allows the intense radiation from massive stars to penetrate deeper into their natal clouds, potentially disrupting a wider area and further influencing the star formation efficiency. The chemical composition of a stellar nursery is not a minor detail. It is a fundamental parameter that dictates the mass, the number, and the very nature of the stars born within it. From the monolithic giants of the cosmic dawn to the diverse stellar populations of today, metallicity is the silent chemist in the background, subtly guiding the universe's great construction project across billions of years. This hidden stellar drama remained invisible for centuries, locked away behind veils of interstellar dust. Our eyes and the optical telescopes that extended them could only see the aftermath, the brilliant stars that had already cleared their dusty cradles. The true birth process was a secret the universe kept in darkness. The breakthrough came when we learned to see with new eyes, to observe the universe in the warmth of infrared light. Cosmic dust, so effective at blocking visible starlight, is transparent to these longer wavelengths. More importantly, the dust itself, warmed by the hidden protostars, glows brightly in the infrared. Telescopes like Spitzer and Herschel became our translators for this hidden language of heat. They revealed the sky ablaze with the warm glow of countless forming stars, each one a bright infrared beacon pinpointing a stellar nursery previously catalogued as an empty void. These observations showed us that star formation is not a rare event, but a continuous, widespread process happening all across our galaxy, hidden in plain sight. While infrared telescopes showed us where the infant stars were hiding, it took an even more specialized eye to see the fine details of their construction. Submillimeter astronomy observes at even longer wavelengths, bordering on radio waves. This allows it to detect the faint thermal radiation from the coldest, densest parts of the molecular clouds themselves. The Atacama Large Millimeter Array, or ALMA, represents the pinnacle of this technology. Perched high in the Chilean desert, its dozens of precision antennas work together as a single, colossal eye on the cosmos. ALMA's incredible resolution acts like a cosmic microscope, peering into the hearts of these dark clouds. It doesn't just see a blur of warm dust, it resolves the intricate structures within. We can now see the flattened accretion disks around protostars in stunning detail, observing the gaps and rings where infant planets are likely coalescing. We can trace the delicate filaments of gas that feed the growing stars and map the vast cavities blasted out by powerful protostellar jets. One of ALMA's most profound revelations was the discovery of ordered motion within these disks. By measuring the subtle shifts in the light emitted by gas molecules, astronomers can chart its velocity. They found clear evidence of Keplerian rotation, where material in the inner disk orbits faster than material in the outer disk, exactly as planets orbit a star. This was direct, observational proof that the swirling disks of theoretical models were real, and that the building blocks of solar systems are in place remarkably early in a star's life. These observational windows have done more than just confirm our theories. They have unveiled a universe far more dynamic and intricate than we ever imagined. We have moved from knowing that stars form to watching them form, frame by frame, in a cosmic movie written in dust and light. This technological revolution has given us a complete stellar formation sequence, transforming points of light on a photograph into a living, breathing narrative of cosmic birth. These violent, chaotic nurseries are now being recreated inside some of the world's most powerful computers. We have built digital laboratories where stars can be born again and again, allowing us to witness their genesis in perfect detail. These are not simple animations, they are sophisticated magneto-hydrodynamic simulations, complex numerical models that weave together the four fundamental forces of star formation. Gravity pulls the gas inward, the fluid dynamics of the swirling, turbulent gas create structure, magnetic fields channel and sculpt the flows, and radiation pressure pushes back with the force of light itself. The goal is to create a virtual universe that obeys all the known laws of physics, and then to watch what emerges from the digital chaos. This approach allows scientists to run experiments that are impossible in the real cosmos, where events unfold over millions of years. We can test different initial conditions, asking what happens if we increase the magnetic field strength or reduce the turbulence. We can rerun the same simulation 100 times with tiny variations, building up a statistical understanding of which outcomes are common and which are rare flukes. These models have become the crucial bridge connecting elegant theoretical predictions to the messy, beautiful reality revealed by our telescopes. For instance, simulations show that the distribution of stellar core masses, the seeds for stars, is not random. It emerges directly from what is known as a turbulent cascade, where energy from large-scale motions in the cloud trickles down to smaller and smaller scales, naturally creating a spectrum of dense knots that matches the initial mass function we observe. The simulations show us the how, revealing the invisible hand of structured chaos sculpting the stellar family portrait. Yet these digital universes face their own cosmic challenges. The most significant is the dynamic range problem. A star like our Sun is nearly a billion times denser than the molecular cloud it formed from. Simulating both the vast 100-light-year-wide cloud and the compact, fiery birth of a single star within it is like trying to model the entire Earth's weather system while also tracking the path of a single falling leaf. It pushes the limits of even our most advanced supercomputers. To overcome this, researchers use clever techniques, like creating nested simulations that zoom in on regions of interest, applying the full force of their computational power to a specific collapsing core while treating the wider cloud in a more simplified way. The results of these computational experiments are profound. They have shown that magnetic fields are not just a minor player, but a dominant architect, preventing a cloud from collapsing into a single, monstrous star and instead fostering the birth of a distributed stellar family. They reveal how protostellar jets are not just byproducts, but essential regulators that carry away angular momentum with stunning efficiency. And they illustrate how radiation from the first massive star in a cluster can blow away the gas reservoir for its siblings, effectively shutting down star formation in its immediate neighborhood. These virtual telescopes peer into the deepest physics of creation, turning the abstract equations of astrophysics into a dynamic, visual story of how every star, including our own, fought its way into existence. The Eagle Nebula's pillars of creation stand as one of the most recognized portraits of cosmic violence and beauty ever captured. This iconic Hubble image is far more than a photograph. It is a dynamic snapshot of a stellar nursery in action, a living case study where creation and destruction occur simultaneously. Those majestic, towering columns are not serene monuments, they are cosmic battlefields. They are being sculpted and eroded by the intense radiation and stellar winds from a cluster of nearby massive stars just outside the frame. This fierce ultraviolet light acts like a cosmic sandblaster, boiling away the less dense gas and slowly tearing the pillars apart. Yet within this apparent destruction lies the seed of new creation. The same radiation that evaporates the outer layers of the pillars also compresses the gas within them. As the outer material is blown away, it pushes inward on the denser, cooler gas at the pillars' hearts, triggering a gravitational collapse that would not have occurred otherwise. This process, called radiatively driven implosion, is how the death of one generation of stars directly sparks the birth of the next. The pillars are not just being destroyed, they are giving birth. Subsequent observations have peeled back the dusty veil to reveal the hidden progeny within. Infrared views from the Spitzer and James Webb Space Telescopes peer straight through the obscuring dust, showing us bright infant stars embedded deep inside the pillars' dense tips. These are protostars, some still actively gathering mass from their surrounding cocoons, while others have ignited and are now shining with their own light. Some of these young stars have even begun to launch their own tiny jets, miniature versions of the colossal outflows that once cleared the cradle for their massive, destructive neighbors. This region perfectly exemplifies the concept of stellar feedback, a self-regulating loop where massive stars dictate the future of their own nursery. The brilliant O-type stars, through their powerful radiation, simultaneously destroy their own birth cloud while triggering a new wave of star formation within the compressed remnants. They are both architects and demolition crews, shaping the ecosystem that will determine which stars form next and where. The pillars of creation are a breathtaking microcosm of the complex ecology found in every stellar nursery, a vivid demonstration of the beautiful and violent interplay of forces that has shaped our galactic neighborhood for billions of years. Just 1,300 light-years away, a sprawling cosmic metropolis is under construction. The Orion Molecular Cloud Complex is our galaxy's premier local star factory, a vast and chaotic region so close that it offers a front-row seat to the entire stellar life cycle. This is not a single nebula but an immense structure, a complex tapestry of dark molecular clouds, glowing emission nebulae, and glittering young star clusters, all at different stages of evolution. Within this one cosmic laboratory, we can trace the journey from a cold, dark cloud fragment all the way to a brilliant, mature stellar society. Its proximity gives us an unprecedented view, allowing our telescopes to dissect the process of star birth with a clarity impossible anywhere else in the universe. We see the entire story written across the sky. The dark lane obscuring the sword of Orion is the Orion Molecular Cloud itself, a cold, dense reservoir of gas and dust where new stars are just beginning to condense out of the darkness. Adjacent to it lies the magnificent Orion Nebula, a glowing cavity of ionized gas that acts as a brilliant showcase for stars in their infancy. This nebula is essentially a single, giant blister on the side of the much larger, invisible molecular cloud, a region where the most recently formed stars have already blown a bubble in their natal cocoon. Deeper within the complex, regions like the Horsehead Nebula reveal the intricate interplay of light and shadow, where pillars of dust resist the erosive power of stellar radiation. By observing this single complex across the electromagnetic spectrum, from radio waves to X-rays, we can piece together a continuous narrative. Radio telescopes peer into the coldest, darkest cores to witness the very first stages of gravitational collapse. Infrared observatories like the James Webb Space Telescope see through the dust to spot the warm, embedded protostars. Finally, optical telescopes show us the dazzling final product, the young stars that have emerged from their dusty wombs to illuminate the nebula. At the heart of the Orion Nebula lies the key to its brilliance, the Trapezium Cluster. This is a tight group of hot, young, massive stars, each one shining with the ferocity of tens of thousands of suns. Their intense ultraviolet radiation is what ionizes the surrounding gas, causing the entire nebula to glow with its characteristic red and green light. These stellar giants are the master sculptors of their environment, their powerful stellar winds carving out the nebula's central cavity and evaporating the gaseous envelopes of smaller, neighboring protostars. This violent feedback dictates the pace of further star formation in their immediate vicinity, simultaneously destroying the nursery that created them while triggering new waves of birth at the compressed edges of their expanding bubble. Our unique vantage point allows us to study the smallest products of star formation in extraordinary detail. In the quieter corners of the Orion complex, astronomers have identified numerous brown dwarfs. These are objects often called failed stars, too small to ignite sustained hydrogen fusion in their cores. Their discovery helps us understand the lower limits of the star formation process. Even more profound is the direct observation of protoplanetary disks, the birthplaces of future solar systems. Hubble and Webb have captured hundreds of these proplyds, many as dark silhouettes against the bright nebula or as glowing rings of dust encircling their infant stars. We can see how the fierce radiation from the trapezium stars is actively boiling away the outer layers of these disks, effectively limiting the potential for planet formation around some stars while perhaps hastening it for others. This nearby complex provides the foundational data against which we test all our theories of stellar genesis. Every process we have discovered, from turbulent fragmentation to jet-driven outflows, finds its clearest and most detailed example within the borders of Orion. It serves as the essential benchmark, the Rosetta Stone that allows us to interpret the fainter, more distant stellar nurseries glimpsed across the universe. By understanding the violent and beautiful cycles of creation here, in our own galactic backyard, we unlock the secrets of how stars and worlds are born everywhere. But beyond the known forces of dust and light, an even deeper cosmic mystery may be at work. The invisible presence of dark matter could be subtly shaping the very first stars in the universe. This controversial idea suggests that in the earliest, densest galaxies, the immense halos of dark matter surrounding them might have influenced how stars were born. Some theoretical models propose that dark matter particles flowing through the cosmos could have been captured by the gravitational pull of forming stars. If these exotic particles accumulated in a star's core, they might have altered how energy moved from the center to the surface, potentially changing the star's internal structure and its ultimate lifespan. This interaction could have created a new class of objects known as dark stars, fueled not just by nuclear fusion, but by the annihilations of dark matter particles themselves. In this scenario, the mutual destruction of dark matter particles would have provided a powerful and persistent source of heat. This extra energy might have supported vast, puffy protostars against gravitational collapse, allowing them to grow to incredible sizes, far larger than any star we see today. The existence of such behemoths would fundamentally rewrite the story of the universe's first light. Detecting this subtle influence, however, is a monumental challenge. Our entire understanding of dark matter rests on its gravitational effects, and we still do not know its fundamental properties. Predicting how it interacts with ordinary stellar material requires assumptions that are, for now, purely theoretical. The signatures of a dark matter-influenced star would be incredibly faint and difficult to distinguish from other astrophysical phenomena. The hunt for this cosmic ghost in the machine now falls to a new generation of observatories. The James Webb Space Telescope, with its unparalleled infrared vision, is searching the distant, early universe for the unique chemical fingerprints of these hypothetical first stars. By analyzing the light from the most ancient galaxies, astronomers hope to find clues, perhaps an unexpected abundance of certain elements or a peculiar luminosity that could only be explained by the presence of dark matter annihilation. Future gravitational wave detectors might also sense the ripples from the collapse of such exotic objects. This speculative connection between the dark and light sectors of the universe represents the absolute frontier of star formation research. It is a reminder that the violent cradles of stars may hold secrets woven from the fabric of the cosmos itself, waiting for the right tools and the right minds to bring them into the light. The story of a star's birth is not written in stone, but in the swirling chaos of its galactic neighborhood. The same fundamental forces of gravity and turbulence play out in radically different ways depending on where in a galaxy a stellar nursery takes root, creating a stunning diversity of stellar families across the cosmos. In the serene, ordered spiral arms of galaxies like our own Milky Way, star formation is a relatively organized affair. Here, the majestic spiral arms act not as physical structures but as waves of compressed gas, sweeping through the galactic disk like a cosmic traffic jam. As giant molecular clouds enter these dense waves, the increased pressure triggers their collapse, orchestrating star formation in brilliant, sequential bursts that trace the galaxy's grand design. This process populates the spiral arms with sparkling clusters and luminous nebulae, the classic signposts of a galaxy actively building its stellar population. Venture into the heart of a galaxy, however, and the rules of stellar birth are rewritten. The galactic center is a realm of extremes, a maelstrom governed by a supermassive black hole and bathed in fierce radiation and powerful magnetic fields. Here, the ambient pressure is millions of times greater than in the quiet disk. This incredible pressure can force giant clouds of gas to collapse directly into stars without first fragmenting into smaller cores, potentially giving rise to a population of unusually massive stars. Some theories even suggest that this extreme environment could produce exotic stellar objects, like massive stars with strange chemical compositions or tightly packed clusters where stellar collisions are a common event. The galactic center is a stellar factory operating under a different set of blueprints, where the relentless pressure forges stars in ways we are only beginning to understand. At the opposite end of the spectrum lie the dwarf galaxies, the small, quiet cousins of majestic spirals. In these low-density environments, with their pristine gas and minimal amounts of heavy elements, star formation is a far more subdued process. Without a rich supply of metals, the gas cannot cool efficiently, making it difficult for clouds to fragment. This often results in a top-heavy initial mass function, where these galaxies produce a greater proportion of massive stars relative to small red dwarfs. The star formation history in these dwarfs is not a continuous process but a series of isolated, single bursts, as if the galaxy only occasionally musters the energy to create a new generation of suns. Then there are the starburst galaxies, the cosmic infernos where star formation reaches a fever pitch. These are galaxies undergoing a spectacular, rapid-fire burst of creation, forming stars hundreds or even thousands of times faster than a typical spiral. A starburst is often triggered by a violent gravitational encounter, a galactic collision or merger that funnels immense reservoirs of gas into a small, central region. This is not a new process but a scaled-up, hyper-intense version of the physics we see in Orion. The same feedback loops are at work, just on a galactic scale. The furious birth of millions of stars creates powerful superwinds, colossal outflows of gas that are blown clear out of the galaxy itself. These winds can eventually shut down the starburst by expelling the very fuel required to make new stars, a dramatic example of a galaxy's star-forming engine ultimately consuming itself. Even the large-scale structures within a galaxy leave their mark. A central bar of stars and gas can act as a cosmic conveyor belt, relentlessly funneling gas inward to feed intense star formation in the galactic nucleus, often creating a brilliant ring of new stars around the center. The variation we observe from the calm disk to the chaotic core demonstrates that while the physics of star formation is universal, its outcomes are exquisitely sensitive to local conditions. This profound connection ties the fate of a single star to the grand architecture of its home galaxy, revealing a cosmos where stellar physics and galactic cosmology are intimately and beautifully intertwined. The universe's very first stars were born into a world of profound simplicity and immense challenge. This was the era of population 3 stars, the primordial pioneers that illuminated the cosmic dark ages. They formed from a pristine soup of only hydrogen and helium, a universe utterly devoid of the heavy elements we now take for granted. This lack of metal was not a minor detail, it was the defining condition that dictated their entire existence. Without the dust grains and complex molecules that act as efficient cooling agents in modern nebulae, these ancient clouds had only one way to shed their gravitational energy: the faint, inefficient glow of molecular hydrogen. This poor cooling meant the collapsing clouds could not easily fragment into small, dense cores. Instead, they were forced to collapse in vast, monolithic chunks. The result, according to our most advanced simulations, was a population of stellar behemoths. Each one of these first stars may have been a colossal giant, containing the mass of hundreds of our suns. Their lives were as brilliant as they were brief, burning through their nuclear fuel in only a few million years before meeting a cataclysmic end. The light from these stellar titans was the first true sunrise of the cosmos, and it forever changed the universe. Their intense ultraviolet radiation began to re-ionize the neutral hydrogen gas that filled all of space, burning away the primordial fog and creating the transparent universe we see today. This was the epoch of reionization, a fundamental phase transition driven entirely by the fierce glare of these first suns, but their most enduring legacy was written in their spectacular deaths. When a population 3 star exhausted its fuel, it did not go quietly. It collapsed and exploded in a supernova of unimaginable power, a hypernova that far outstripped any stellar death in the modern universe. In the heart of these explosions, for the first time in cosmic history, nuclear fusion forged elements heavier than helium. Carbon, oxygen, silicon, and iron were blasted out into the void, polluting the pristine gas with the seeds of all future complexity. This initial enrichment was the crucial turning point. The universe was no longer pure. It now contained the raw materials for dust grains for rocky planets and for the long, stable lives of future, smaller stars. The search for these stellar ancestors is one of astronomy's greatest quests because they lived and died so quickly. We cannot see individual population 3 stars with our current telescopes. They are ghosts from the dawn of time, yet we hunt for their chemical fingerprints in the most ancient stars of our own galaxy, tiny, long-lived dwarfs that formed from gas enriched by just 1 or 2 of those first supernovae. Their unique elemental patterns are like cosmic archaeology, revealing the composition and mass of the long-dead giants that spawned them. We are also pushing our observatories to their limits, using the James Webb Space Telescope to peer back to the very edge of the observable universe, searching for the collective glow of the first star clusters or the unique signatures of their supernova remnants. Supercomputer simulations are our time machines for this era, recreating the radically different physics of a metal-free cosmos. These models start with the subtle density fluctuations left over from the Big Bang and then let gravity, fluid dynamics, and primitive chemistry work their magic. They show us how the first protostellar cores formed without the help of dust, and how their accretion disks might have behaved under such extreme conditions. The story of population 3 stars is the Genesis chapter for everything that followed. Their violent lives and explosive deaths set the initial conditions for the cosmic cycle of birth and rebirth that continues to this day, a cycle that ultimately made our own metal-rich sun and planet possible. Yet even on the lowest rung of the stellar ladder, the universe finds a way to blur the lines. Brown dwarfs are cosmic enigmas, objects that begin their lives like stars but ultimately fail to ignite. They are born from the same turbulent fragmentation that creates their brilliant stellar siblings, condensing out of collapsing molecular clouds, but their story diverges at a critical threshold. A brown dwarf simply does not gather enough mass, typically less than about 80 times the mass of Jupiter, to generate the core temperatures and pressures needed for sustained hydrogen fusion. Without this central engine, they cannot become true, long-lived stars. They are the almost stars, the could-have-beens of the cosmos, occupying a mysterious realm between star and planet. For a brief, youthful period, however, they do manage to spark a different kind of fire. When a young brown dwarf first contracts, its core becomes hot enough to burn deuterium, a heavy isotope of hydrogen. This deuterium burning phase is a faint, short-lived flicker, lasting only a few million years. It provides a crucial distinction, a developmental marker that separates a young brown dwarf from a gas giant planet like Jupiter, which never experiences any form of internal fusion. After this brief flare of activity, the brown dwarf's fate is sealed. It has no lasting energy source. It simply cools and fades over billions of years, gradually dimming from a dull red glow to a virtually invisible infrared signature in the darkness of space. This cooling process presents a major challenge for astronomers trying to find them. Since they emit very little light and are often isolated in space, brown dwarfs are difficult to detect, acting like cosmic ghosts hiding in plain sight. Their existence pushes our theoretical models to the breaking point. How does the turbulent collapse of a cloud produce an object with so little mass? What physical process determines this lower limit for star formation? The answers are still emerging, but observations are revealing a surprising truth. Brown dwarfs, despite their solitary reputation, are often found in pairs. We have observed binary brown dwarf systems, 2 failed stars locked in a gravitational dance. Some even possess their own circumstellar disks of gas and dust, miniature versions of the protoplanetary disks that form planets around true stars. This suggests their formation pathway is fundamentally stellar, a product of the same cloud fragmentation and disk physics that builds suns, just on a much smaller scale. These substellar objects complete the mass spectrum of products from stellar nurseries, from the brilliant, short-lived O-type giants hundreds of times more massive than our Sun, down to these dim, cooling dwarfs only a few times heftier than Jupiter. The star formation process generates a continuous spectrum of objects. Brown dwarfs are the vital missing link, demonstrating that the universe does not deal in strict categories, but in a beautiful and seamless continuum. They force us to expand our definitions, reminding us that the violent cradles of stars are factories of endless variety. A stellar nursery's greatest creation is also its executioner. The brilliant stars born within these clouds soon unleash the very forces that will tear their cradle apart. This dispersal is the final, necessary act in the life cycle of a molecular cloud, a dramatic clearing of the cosmic stage. The process begins with the most massive stars in the newborn cluster. Their intense ultraviolet radiation floods the surrounding gas, energizing it to the point where electrons are torn from their atoms. This ionization heats the gas to temperatures of 10,000 degrees, causing it to expand violently and blast away from the star. Simultaneously, these stellar giants drive powerful supersonic winds, streams of charged particles that pour from their surfaces. This 1-2 punch of radiation and wind carves vast, growing cavities within the cloud, like bubbles boiling in a cosmic pot. We see this beautifully in regions like the Rosette Nebula, where a central cluster of hot stars has blown a gigantic hole in the center of its parent cloud, leaving a ring of glowing gas and dark dust that marks the expanding edge of the destruction. The speed and completeness of a cloud's dissolution are dictated by its most powerful children. A cluster that forms even a single O-type star will see its nursery obliterated in just a few million years. The ferocious output from such a behemoth can evaporate the surrounding gas with astonishing efficiency. In contrast, a cloud that only produces smaller, gentler stars may persist for tens of millions of years, its gas slowly and quietly dissipated by their milder combined influence. This relationship creates a natural timer on star formation within any given cloud. The clock starts ticking the moment the first massive star ignites, and the countdown to dispersal begins. This violent feedback ensures that star formation is remarkably inefficient. On average, only a small fraction of a molecular cloud's immense mass, typically between 1 and 10%, is ever converted into stars before the rest is blown back into interstellar space. The vast majority of the gas is returned to the galactic reservoir, destined to one day become part of a future nursery. Observing the sky reveals this entire life story written in stellar associations. We can see every stage, from deeply embedded clusters like the one hidden within the Orion molecular cloud, where newborn stars are still shrouded in their thick, dusty womb, to exposed open clusters like the Pleiades, which have already cleared away their natal gas and now shine as a brilliant, naked family of stars. The final, most dramatic act of dispersal comes from supernova, when the most massive stars end their short lives in catastrophic explosions. The resulting shockwaves deliver the coup de grace to any remaining cloud structure, sweeping up and scattering the last vestiges of gas and enriching it with newly forged heavy elements. This finite lifespan for every stellar nursery means that star formation across a galaxy occurs in distinct, punctuated episodes. It is not a continuous process, but a cyclical rhythm of cloud assembly, collapse, and destruction. This beautiful, destructive cycle, where stars are both the products and the agents of their own cradle's demise, is the fundamental engine that drives the chemical and dynamic evolution of entire galaxies. Our solar system began not in quiet solitude, but within a bustling stellar metropolis. We can reconstruct our own violent nursery by reading the forensic evidence locked inside ancient space rocks. Primitive meteorites, the unaltered building blocks of our planetary system, contain microscopic grains that predate the Sun itself. These presolar grains carry distinct isotopic signatures, chemical fingerprints that point to a dramatic origin. The presence of specific isotopes like aluminum-26 and iron-60 indicate that a massive, short-lived star lived and died nearby, seeding our natal cloud with its explosive remains just before our Sun ignited. Our entire system was literally built from the ashes of a supernova. This celestial archaeology reveals that our Sun was not an only child. It was born in a rich, open cluster, surrounded by thousands of other stellar siblings. The very architecture of our solar system supports this idea. The orderly arrangement of planets, the sharp divide between the inner rocky worlds and the outer gas giants, and the existence of a distant Kuiper belt all point to a formation within a dense, but not overwhelmingly chaotic, stellar environment. The gravitational influence of our stellar siblings would have been gentle enough to allow our protoplanetary disk to settle into a stable structure, yet strong enough to help sculpt its final form. The fact that our Sun now drifts alone is a testament to the impermanence of these stellar families. Over hundreds of millions of years, the gentle gravitational tugs between stars and the much stronger pull of the galaxy's spiral arms slowly tore the cluster apart, scattering its members across the Milky Way. Our Sun's siblings are now lost among the billions of other stars in the galactic disk, their shared origin story erased by time and distance. We can model this dispersal by studying young clusters we see today, like the Jewel Box or the Pleiades. These glittering families show us the vibrant, crowded conditions our own system experienced in its infancy. They demonstrate how stellar neighbors can gravitationally stir protoplanetary disks, potentially hurling comets inward to deliver water and organic compounds to young worlds. The specific conditions within our natal cluster were a cosmic prerequisite for life. The supernova that enriched our cloud with heavy elements also provided the radioactive isotopes that heated early planetesimals, driving the geochemical cycles that ultimately made Earth a habitable world. Our solar system's quiet present belies a dramatic and interconnected past, a heritage of stellar violence and kinship that made our existence possible. The universe's star-forming prime is a chapter written deep in the past. Billions of years ago, our cosmos was a far more prolific nursery, a place where stellar birth unfolded at a breathtaking pace. The most intense era of creation occurred roughly 10 billion years ago, a period astronomers call cosmic noon. During this prolific age, galaxies were churning out new stars at a rate 10 or even 20 times faster than they do today. We see this vibrant history by looking far out into space, and therefore back in time, at distant galaxies whose light has been traveling for billions of years to reach us. Their youthful forms are ablaze with the brilliant blue light of countless massive, short-lived stars, the unmistakable signature of a stellar baby boom on a cosmic scale. This frenetic pace of creation could not last forever. The decline from that ancient peak to our current, more sedate era tells a story of changing resources and environments. Primary fuel for star formation, cool hydrogen gas, was far more abundant in the early universe. Galaxies were richer in this raw material, and frequent, dramatic collisions between them were common. These galactic mergers violently shook up vast reservoirs of gas, triggering immense waves of gravitational collapse and igniting furious starbursts. Over time, as the universe expanded and evolved, this primordial gas was gradually locked away inside stars or blown out into intergalactic space. The remaining gas reservoirs in modern galaxies are simply more depleted, and while mergers still happen, they are less frequent than in the crowded, chaotic universe of the past. The rate of stellar birth is also slowed by powerful feedback. The very stars created in those early bursts, especially the massive ones, eventually exploded as supernovae. Their violent deaths and the fierce radiation from their lives heated and expelled surrounding gas, making it harder for new stars to form. This self-regulating mechanism gradually put a brake on the rampant star formation of cosmic noon, steering galaxies toward a more measured pace of creation. To measure this grand timeline, astronomers use clever proxies that act as stellar census takers. Since the brightest, most massive stars emit most of their light in the ultraviolet, detecting this UV glow from a galaxy provides a direct count of its recent stellar births. However, young stars are often hidden in dusty cocoons. That same dust absorbs the ultraviolet light and re-radiates it as infrared warmth. By combining ultraviolet and infrared observations from space telescopes, we can account for both the visible and the hidden stellar newborns. For the most dust-shrouded stellar factories, radio telescopes tune into the faint emission of carbon monoxide gas, which traces the dense molecular clouds where stars are actually forming. Each of these methods provides a different piece of the puzzle, allowing us to assemble a coherent picture of star formation rates across billions of years. This cosmic history is far from completely written. The next generation of observatories, like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, are designed to peer back to the very dawn of the first galaxies and stars. They will map the rise of star formation from the cosmic dark ages through its glorious peak and into its gradual decline. The changing star formation rate is more than a historical record. It is a fundamental evolutionary pattern of the cosmos. It reveals how the universe's capacity for creation is shaped by its available resources and its own turbulent history. A grand cycle that dictates the rise and fall of stellar generations across the eons. The James Webb Space Telescope has ripped away the final veil. This revolutionary observatory, with its piercing infrared gaze, is transforming dark blurs on an astronomer's screen into vivid, dynamic portraits of stellar birth. Its unprecedented sensitivity and resolution act as a cosmic microscope, allowing us to witness stages of star formation that were pure theory just a generation ago. In nearby nurseries like the Orion Nebula, Webb does not just see the young stars, it dissects the very process of their creation. It reveals the intricate structures of protoplanetary disks in stunning clarity, showing us the lanes and gaps where infant planets are likely coalescing. We can now trace the delicate filaments of gas that feed these growing stars, mapping the complex web that connects a newborn sun to its natal cloud. But Webb's vision extends far beyond our galactic backyard. It peers across cosmic time, capturing the faint, red-shifted light from the earliest galaxies. There, in the primordial universe, it is hunting for the unique chemical signatures of the first stars, the colossal population, three giants whose explosive deaths seeded the cosmos with its first heavy elements. By comparing star formation in these infant galaxies to the processes we see in the modern Milky Way, we are learning which physical laws are universal and which are shaped by a galaxy's age and environment. The telescope's data is not just confirming our models, it is actively challenging and refining them. For instance, Webb's detailed observations of protostellar outflows are revealing that these jets are even more powerful and structured than we predicted, suggesting our understanding of how magnetic fields launch and collimate them is still incomplete. Its ability to see the frigid, dense cores just beginning to collapse is helping us pinpoint the exact initial conditions that determine whether a cloud fragment will become a brown dwarf or a brilliant giant. This is more than an upgrade. It is a quantum leap in our quest to understand stellar genesis. Every new image from Webb is not just a picture, it is a chapter in the universal story of creation, forcing us to rewrite our textbooks with a deeper, more nuanced understanding of how every star, including our own, fights its way into the light. This same swirling disk of dust and gas, the stellar cradle that feeds a young star, is also the birthplace of its future planets. The violent processes that forge a star directly set the stage for the assembly of entire solar systems, transforming a single event into a dual genesis. The protoplanetary disk is more than just a construction site. It is a cosmic sorting facility where temperature, gravity, and time work together to build worlds. The disk's temperature decreases dramatically with distance from the hot, central protostar. Close in, where temperatures are searing, only metals and rocky minerals can remain solid. This hot inner zone becomes the forging ground for terrestrial planets, small, dense worlds like Earth and Mars. Farther out, beyond what is called the frost line, temperatures plummet enough for volatile compounds like water, ammonia, and methane to freeze into solid ice grains. These ices act as additional building material, allowing the cores of gas giants to rapidly accumulate vast amounts of material, growing to immense sizes. The star's own identity dictates the potential of its planetary family. A star's mass is the ultimate dictator of its lifespan and luminosity, which in turn controls the habitable zone, the orbital region where liquid water could exist on a planet's surface. More massive, brilliant stars have wider but shorter-lived habitable zones, while long-lived, faint red dwarfs have habitable zones so close that planets within them may be tidally locked, with one side in perpetual daylight and the other in eternal night. The chemical richness of the Nursery, its metallicity, also plays a profound role. A star system born from a cloud enriched with heavy elements from past supernova has more solid material available to build planets. We see this correlation clearly in exoplanet surveys, which find that stars with higher metal content are significantly more likely to host gas giant planets, simply because there was more raw material for their massive cores to form. Even the star's social situation matters. In a binary star system, the gravitational tug of a companion star can disrupt the protoplanetary disk, truncating it or stirring it into unstable orbits. Planets that do form in such systems often have wide, eccentric paths, or they may orbit one star in a tight, stable circuit, forever influenced by their distant stellar sibling. The final architecture of a planetary system is a permanent record of its chaotic birth. The spacing of planets, the presence of asteroid belts, and the tilt of planetary orbits all preserve clues about the dynamic conditions within the primordial disk. When we look at our own solar system, we see these fingerprints everywhere. The orderly spacing of the planets suggests a relatively calm and stable disk. The asteroid belt between Mars and Jupiter marks a region where the gravitational influence of the giant planet Jupiter prevented a single world from coalescing. The Kuiper belt, a distant ring of icy bodies, is the leftover debris from the outer solar system's construction. Exoplanet discoveries have revolutionized this understanding, revealing an astonishing diversity of systems that challenge our solar system's model. We have found hot Jupiters, gas giants orbiting impossibly close to their stars, which must have migrated inward from their birthplaces in the cold outer disk. We have discovered super-Earths, rocky planets larger than our own, which are absent from our solar system but common throughout the galaxy. Each of these exotic configurations tells a story about the conditions in their natal nursery, whether it was a dense, dynamic environment that forced planets to dance and migrate, or a quieter one that allowed for a more orderly construction. The journey from a turbulent cloud of gas to a stable star with a family of planets is a single, continuous story. The same forces of gravity, angular momentum, and chaos that sculpt a star simultaneously write the blueprint for its future worlds, forever linking the fate of a sun with the potential for the planets that orbit it. Yet another invisible force weaves through these stellar nurseries, a relentless rain of high-energy particles from deep space. Cosmic rays are the atomic nuclei of elements, accelerated to nearly the speed of light by the shockwaves of supernova explosions and other violent cosmic events. They are the ultimate interstellar travelers, and when they pierce the dark, cold heart of a molecular cloud, they become subtle architects of star birth. Their primary tool is ionization. As a cosmic ray particle smashes into a cloud, it can strip electrons from the neutral hydrogen molecules and atoms that make up the vast bulk of the gas. This creates a sparse population of charged particles, ions, drifting within a sea of neutral material. This slight electrification is far more significant than it sounds. It provides a crucial anchor for the cloud's magnetic fields. The magnetic field lines, which are frozen into the ionized component of the gas, can now exert a drag on the neutral atoms and molecules through a process called ion-neutral friction. This magnetic coupling acts as a brake on the collapse, providing a form of support that helps the cloud resist gravity's relentless pull. The rate at which this support leaks away is governed by ambipolar diffusion, the slow drift of neutral particles past the magnetically locked ions. Cosmic rays directly control the dial on this process. A higher flux of cosmic rays means more ionization, a stronger magnetic coupling, and a slower rate of ambipolar diffusion. This stretches out the timescale for a cloud's collapse, potentially delaying star formation and allowing for a more gradual, structured assembly. In regions with lower cosmic ray flux, the magnetic support weakens more quickly, potentially allowing gravity to win faster and leading to a more rapid burst of stellar births. This suggests that the efficiency of star formation across a galaxy could be subtly influenced by the local intensity of this cosmic particle rain. Astronomers are now finding evidence that this flux is not constant. Measurements suggest that cosmic ray densities can vary significantly throughout a galaxy, often correlating with regions of past or present stellar activity. In the bustling central regions of galaxies where supernovae are more frequent, the cosmic ray flux is likely much higher. This could mean that star formation in these crowded environments is subject to a different regulatory rhythm than in the quiet, outer galactic suburbs. Theoretical models are beginning to incorporate this energetic feedback, exploring how cosmic rays might affect the stability and fragmentation of clouds. Some simulations indicate that by modulating the strength of magnetic support, cosmic rays could influence the initial mass function itself, subtly shifting the statistical odds toward creating more low-mass stars or more high-mass giants. When we piece together the entire story, from turbulent gas to magnetic fields, and now to this rain of energetic particles, we see that a stellar nursery is a system of exquisite balance. Cosmic rays represent a critical, though often overlooked, environmental factor. They complete our understanding of the external forces that work in concert with gravity's deep pull, together writing the complex and beautiful recipe for how stars are born. Our galaxy's brilliant era of star formation is slowly drawing to a close. The Milky Way currently forges 1 or 2 new suns each year, but this steady pace is destined to falter. The primary reason is a simple cosmic fuel shortage. Over billions of years, our galaxy has converted a vast portion of its primordial hydrogen gas into stars, and the remaining reserves are not being fully replenished. While supernova and stellar winds do return some enriched material to the interstellar medium, a significant fraction becomes permanently locked away in long-lived, low-mass stars, white dwarfs, and neutron stars. This gradual exhaustion of raw material means the star formation rate must inevitably decline, a quiet fading of our galaxy's creative power. We can already see this future written in the aging populations of other spiral galaxies, where the brilliant blue glow of young star clusters gives way to the softer, redder light of ancient stellar communities. The Milky Way's destiny is to become a quieter, more sedate place, dominated by the faint, enduring embers of red dwarfs that will shine for trillions of years. Yet this gentle decline will not be entirely smooth. Galactic dynamics promise a few final, dramatic acts. In roughly 4 billion years, the Milky Way is set to collide with the Andromeda Galaxy. This monumental event will violently shake up the remaining gas reservoirs in both galaxies, funneling immense clouds together and triggering a brilliant but short-lived starburst. For a time, the star formation rate could spike to dozens of solar masses per year, creating a spectacular but fleeting renaissance of new star clusters and massive, brilliant suns. This fiery climax, however, will only hasten the final exhaustion. The combined galaxy, often called Milkomda, will likely expel or consume the last of its usable gas in this furious burst, after which the long twilight will truly begin. The changing nature of stellar birth will fundamentally alter the galaxy's character. Without frequent supernova from short-lived massive stars, the interstellar medium will receive fewer new heavy elements. The formation of rocky, terrestrial planets like Earth, which rely on this chemical enrichment, will become increasingly rare. Future planetary systems will instead be built from the recycled ashes of earlier generations, potentially leading to worlds with very different geologies and atmospheres. This grand trajectory from a vibrant, gas-rich youth to a fuel-starved old age is the natural life cycle of a spiral galaxy. By observing the red and dead galaxies in the distant universe, we are essentially looking at the future of our own stellar home, a quiet, mature state where the furious cradles of star formation are finally at rest. For all we have learned, the violent birth of stars remains a story with profound gaps. We can trace the journey from a collapsing cloud to a blazing sun, yet the very first pages of that story are still blank. We do not truly understand how the immense molecular clouds themselves are assembled. These colossal structures, light years across, materialize from the thin, diffuse gas of interstellar space, a process that remains one of astronomy's deepest puzzles. What forces gather this tenuous material and weave it into the dense, turbulent nurseries where stars can eventually form? The answer likely involves a subtle interplay of galactic dynamics, gravity, and the sweeping pressure of spiral arms, but the precise recipe is still unknown. This leads directly to another fierce debate among astrophysicists. Once a cloud exists, what holds it up? Is it the chaotic supersonic turbulence creating a structured support against gravity's pull? Or is it the invisible scaffolding of magnetic fields providing a springy resistance that slows the collapse? The truth is probably a complex combination of both, but determining their relative importance is a central challenge. Observations from telescopes mapping polarized light offer clues, yet the final verdict on this cosmic balancing act remains elusive. Perhaps the most puzzling mystery is the stunning consistency of the initial mass function. From the crowded core of our galaxy to the faint, primordial dwarfs at the edge of the observable universe, the statistical rule that governs the distribution of stellar masses appears to be nearly universal. How can such a predictable pattern emerge from what should be a chaotic and environment-dependent process? Why does a turbulent cloud in a modern spiral arm produce the same family portrait of stars, from red dwarfs to blue giants, as a cloud in a metal-poor dwarf galaxy? This universal bias toward small stars suggests a fundamental physics that operates the same way everywhere, a hidden hand guiding the chaos toward a predictable outcome. The ultimate frontier lies at the dawn of time with the very first stars. We have theoretical models for these population 3 behemoths, but we lack direct observational proof of their existence or their exact properties. How did the universe transition from forming those isolated, colossal giants to the efficient, clustered production of diverse stars we see today? What was the precise trigger that moved star formation from its primordial, monolithic mode to the modern, recycling era we now observe? Each of these unanswered questions is a beacon on the map of human knowledge, guiding the next generation of telescopes and supercomputer simulations. They remind us that for every cosmic mystery we solve, the universe reveals a deeper, more beautiful layer of complexity waiting to be understood. This entire cosmic journey, from a silent cloud's first shudder to a star's final stability, reveals a universe built on beautiful violence. We have traced the collapse of formless gas, sculpted by turbulence and magnetic fields into the spinning disks that birth both stars and planets. We have witnessed the protostar's furious struggle, battling its own light to gather mass and unleashing jets to carve out its space. The outcome is a brilliant main sequence star, a stable beacon that will shine for millions or billions of years, its identity and potential planetary family forever shaped by the chaotic cradle that created it. These turbulent nurseries are nature's ultimate factories, transforming the simplest elements into complex stellar systems through forces of unimaginable power. To understand this process is to do more than satisfy a scientific curiosity. It connects us directly to our own cosmic origins, for our sun and our planet were forged in just such a tempestuous environment. The heavy elements that compose our world and our bodies were scattered by long-dead stellar giants, their explosive deaths providing the raw materials for our existence. We are literally made of stardust, the legacy of this endless cycle of creation and destruction. As our telescopes peer deeper and our simulations grow more sophisticated, each mystery we solve unveils new questions waiting just beyond the light. The next great observatory or computational breakthrough will undoubtedly rewrite another chapter in this story. So the next time you look up at the night sky, remember that you are not just seeing points of light. You are witnessing the triumphant outcome of a dramatic, violent genesis. Each star is a testament to a battle won against chaos, a reminder of our profound connection to the endless cosmic dance that stretches from the past into all of our future